All right. Uh, Hello, everyone. Welcome to the online AI seminar series. We are very pleased to have Professor Laura Leal Taché today with us to talk about some of recent cool stuff she has been doing. Laura is a tenure track professor at the Technical University of Munich, where she's leading the Dynamic Vision and Learning Group. Before that, she had had multiple research positions at ETH Zurich, Technical University in Munich, University of Michigan Ann Arbor, and Northeastern University. She is recipient of Sofia Kowalewska Award for her project on Social Map. But today she's going to talk about object tracking and the impact on data privacy and some of the work in that direction also. Thank you, Laura. All yours.
Thank you, Ayus, for the introduction, and thank you also for organizing this. It has been wonderful to see like all the different works that you're doing, like super interesting. So I hope that you can also find our works interesting. So most of the research that I do revolves around multiple object tracking since my PhD. And so today I want to talk about two aspects of multiple object tracking. So let's see, yeah. So the first one is essentially how to include more learning into multiple object tracking. So how to really leverage the power of deep learning that has been revolutionizing all kinds of image classification, detection fields. How can we actually take advantage of that in multiple object tracking? And the second topic I want to talk about is about data privacy, which is kind of a new topic that we start to focus on now in multiple object tracking. So let's start by introducing the topics. I'm sure you're all familiar with it, but multiple object tracking is the goal of detecting and tracking all the objects in a scene. And we focus typically on people tracking. So people have very interesting movements. They are hard to predict. They have their own will. So working on tracking pedestrians is actually really interesting. And the classic way of doing this, as you will know, is tracking by detection. So essentially what you do is you first apply a detector on each frame of a video to obtain a series of proposed locations. So possible locations where an object of interest might be. And then in a second step, usually completely separate, you infer the temporal coherence. So essentially you put, for example, a graphical model on top of your detections and you try to establish associations. So for example, the trajectories that are recovered here, the blue trajectory, the orange trajectory. Of course, when you start doing data association, you start to see the problems of detection, right? So you might have false positives, false negatives. And this is typically what we need to focus on when we do data association. And so the question that we started asking ourselves 3-4 years ago was, how can we actually go progressively towards end-to-end learning in MAUT, right? So for now, it's completely separate. There's this separation of detection and data association. So any learning that we put in there, it's not really going to take a step forward towards end-to-end learning, right? So we're trying, first of all, to include more learning into both steps. And second of all, to put both steps more together in a unified way so that we can finally train an end-to-end model. So since we are talking about the two steps, we're going to look at both of them separately, and we're going to try to use more learning for both steps, and also at the same time, always keeping this idea of this Uber system that kind of does everything end-to-end. So this work, I didn't know actually that it was very much used by a lot of people at CMU. So now I feel a little bit, it's kind of redundant to explain it, but it's the work that we did in ICCV 19. And it's about taking a deeper look at how regression-based detectors work. So essentially for a region, regression-based detectors, they take the input image, extract features with convolutions. And then the idea is that, of course, we're not interested in the whole image, but in certain regions that are interesting for us, for example, that might contain a pedestrian. And so at the end of the day, what we're going to do is through region pooling, we're going to analyze only that part of our feature map. We're going to put a classification head on top that tells us the class of the object and a regression head on top. Now, the interesting thing for me is the regression head, right? So what does the regression head do? The regression head essentially takes a bounding box at the input image that is potentially badly positioned, right? It's kind of close to the true position of the bounding box, but it's not perfect. And it regresses it to fit tightly around the object. So after seeing this behavior, one thinks, well, this is actually not too different from what we want to do in online tracking, right? So by online tracking, I mean we're looking at different frames, like consecutive frames, and we want to infer where did the detection go from one frame to the next. And so if we think about it, an object is not typically jumping around from one part of the image to the other. There's kind of a smooth motion. And so if we have this smooth motion assumption, we can just use the regressor of the detector to do tracking. And this is the main idea behind our paper, Tracking Without Bells and Whistles, and our method Tractor, which essentially takes a detector and converts it into a tracking mechanism. So the idea is super simple, right? We have frame t+1. We take the detections of frame t, so the previous frame, as our proposals, thinking always about, for example, a faster RCNN type of architecture. And then we know that these detections are going to be quite close to the detections that we want to obtain at frame t+1, because the object has not moved too much. And so essentially, with the bounding box regression, we don't even need to retrain it. Just with the faster RCNN bounding box regression, we can get the correctly positioned boxes. So, okay, this we know. We know that the detector works like this, but the question is, are we actually doing tracking like this? So does this detector have actually tracking capabilities? And in order to say whether we're doing tracking or not, we have to ask the question, or let's say we have to ask ourselves, can we answer this question, right? So if I can know where a certain detection with ID 1, and here the IDs are represented by the different colors. So if I can answer the question, where did the red box go in the next frame, then I can actually do tracking. And of course, since I know exactly where the bounding box has been regressed to, I can then make the assumption that the two boxes share the same identity. So this is a super simple framework, right? We didn't even train anything, right? We didn't even do anything. So let's start by analyzing what are the pros and cons of such a simple method. So first of all, again, we don't really need to retrain anything. There's extremely well-trained regressors in object detection frameworks. And so the bounding boxes that we get are super well positioned. And this is already a challenge in tracking because, of course, the evaluation depends also a lot on the intersection over union. So having well-positioned bounding boxes is always a plus. Now, the other pro is that if you need to retrain your tracker, you can also train it on still images like faster RCNN train. So for example, when we need to deploy it for cell tracking, we have very few videos with annotated cells moving around, but we might have a bit more variety of images. So now we don't really need to have this super costly labeling by doctors or by biologists. We can just say, label a few images, and then I will train my detector, and suddenly you also have a tracker. And the other pro, of course, is that it's online, right? So you just process frame by frame. So Tractor is actually quite fast once you optimize the code. But of course, there's a series of cons that we cannot avoid, right? So I would argue it's not really a tracker, right? Because the model has no notion of identity. So it's for us, just walking around, it's very, very likely that the detection just snaps to the wrong pedestrian, right? So Tractor in the most vanilla version has no notion of identity. And so in crowded spaces, it gets confused easily. Now, another con is that as any online tracker, once the track is killed, then if the target, for example, becomes occluded, then there is no way to recover for those occlusions. So we need kind of a mechanism to close small gaps in the case that we can run it as in an offline setting, or at least recover the identity through small gaps and occlusions. Now, for both of these cons, we have the first version of Tractor++. So the first plus is a re-ID method. Basic Siamese architecture detects whether two detections represent the same person and then assigns the same ID. And this works actually quite well when the method gets confused in crowded spaces, when we can verify actually the ID, or to close these small gaps. And I'm going to put a lot of emphasis on small, because we cannot recover gaps of 200 frames. That creates way too much, like a lot of identity switches. Now, a third con is that, as I said, there is a very, very strong assumption that the box shifts only by a small quantity. So there is a smooth motion assumption. The target cannot jump from one place to the other. And therefore, if we have large camera motions, or if the objects are moving a lot due to, for example, low frame rate, then the method doesn't work. Like it's not really capable of regressing to a position that is really far away. But for this, we have very strong motion models that have been developed in computer vision, camera motion models. These help actually a lot, or even person motion models if we actually are dealing with a video with low frame rate. And this, also helps a little bit in filling the small gaps and occlusions. So it turns out that with these two, let's say, flavors on top of our tractor, we get actually quite a boost in performance. And I would like to point out only the boost that we have in identity switches. So the number of identity switches in our ablation studies has been reduced considerably. Now, we don't care too much about the increase in accuracy here, because most of the increase in accuracy in MOTA comes from the identity switches. But what we really want to point out here is that with such a simple method and simple techniques of re-ID and motion model that other methods are using anyway, we can actually get really good identity preservation. But the main question to answer, of course, was, okay, how do you compare with state of the art, right? I mean, tracking has been a field that has been studied for like lots of years. So there's lots of methods out there, really complex methods. Why should this super simple method work much better? Well, it turns out that we were easily state of the art, and the method works surprisingly well. Again, here I'm showing only Tractor++, so with the motion model, with the re-ID. And it is important to note the idea of one measure. So basically this idea of identity preservation. For this measure, even though we have super simple re-ID, we are still state of the art or second in the case of Mod 17. So even though everyone is using re-ID, and most of the methods that we show here in this table actually do have a Siamese network for re-ID, that re-ID is not really exploited to the maximum. And so inside Tractor, it can really shine. So of course, after seeing this, I mean, this seems like a joke, right? I mean, we didn't train anything. We took a pre-trained detector, couple of re-ID motion model tricks, and now suddenly we're state of the art, right? So the question is, well, what is everyone else doing, right? I mean, these are top researchers, they're doing good work in tracking. And so the bulk of our paper was actually about analyzing these results, right? What is everyone else doing? And what are the kind of problems that everyone else is tackling? And what are the problems that Tractor is actually tackling? So the first thing that we do is we axis given the bounding box visibility. So the idea behind this plot is that essentially what we're doing is we're doing redetection, right, with some form of identity preservation. So if the target is not really visible, then our method should be really bad. That was our initial assumption. I'm also going to plot here, I'm going to draw attention to these bars. And we have discussed this also with in one of the talks with the students, that actually there's not really so many tracks that are occluded, right? So there is a small percentage of ground truth bounding boxes that are completely occluded, but most of the bounding boxes actually have 100% visibility. And as you can see, all the methods are really performing well here. By the way, the distribution of occurrences in ground truth is depicted by the thick bars, the thick turquoise bars. And all the thin bars essentially represent the different methods that we're comparing. And so our method, the vanilla tractor and the tractor plus plus, are represented by these yellow and blue bars. And so one thing that I want to draw attention to is that when we have a really large visibility, all the methods work really well, right? So we can have strong appearance models, strong re-ID. So all the methods perform rather well. And since most of the data is actually highly visible, then actually improving tracking results becomes really hard, because everyone is fighting for the highly visible boxes. There are a lot of them, but everyone is doing well on those. And why we're actually doing much better than other methods is because we work well in this range between 0.3 and 0.7 visibility, where all the other methods start to crash. So you can see here a really, really large difference between the tractor and tractor plus plus and all the other methods, which completely collapse, starting by a visibility of 0.6, so 60%. And you might wonder, well, I mean, there are all these methods that actually use a huge graph on top of the detections, perform offline tracking, are able to look into the future, to fill in the gaps. So some of these methods are depicted here, and still these methods are not capable to recover from partial occlusions. So that's a huge problem in tracking, right? And I might argue that this is the problem in tracking, because if the bounding box is visible, essentially once you have a detection, your tracking becomes much easier. And when tracking becomes really important is when the bounding box visibility starts to drop, and then you have to take the temporal coherence, the temporal information into account. So if all the tracking methods are not really doing this, then the question is, well, you know, are they really tackling the tracking problem? And so what we learned essentially from this paper is that no one is really tackling the hard problems in tracking. So the coverage of large gaps in detections due to occlusions, due to crowded scenes, or due to essentially illumination conditions that don't allow a detector to work, no one is really leveraging the temporal information to cover these large gaps. And same with partial occlusions. And of course, there is an inherent problem of tracking small targets because we have very, very few detections, very sparse detections on a trajectory. And therefore, it is much more expensive for a tracker to recover these trajectories. And it would create a lot more ghost trajectories. So essentially your MOTA, your accuracy would not improve, and you would create more ghost trajectories than actually real trajectories. And so we figured that basically everyone is just marginally improving what we call the easy scenes. So the scenes with high visibility, with few interactions. And this is essentially why we have seen just a small increase, like 2 percentage points in the last 2 years of Mod 16. So this kind of change now, I have to say, like, I'm happy that this is because of the tractor appearance. So we've had quite some success and people are really building on top of tractor, and this has pushed the accuracy by quite a lot. But for the last 2 years, was tiny improvements on easy scenes. So essentially what we propose to do, we propose to say, well, let's use the detector as much as we can. Let's use it as a tractor. This can handle the easy scenes, the small occlusions. This is easy, done. We use basic re-ID, basic motion model, and we can get to a easy, state-of-the-art, and then we can start focusing on tracking, right? So tracking should really be about the harder cases, the long occlusions, and the extremely crowded scenes where a detector is just not enough. So with this, I want to now focus on the tracking part, right? So Tractor is already covered, works really well. This is the most we can get out of a detector. So let's start doing really tracking now and tackling these problems. And this is where we take another look at the tracking by detection, right? So as I said, it divided the tracking into two parts, the object detections and the data association. So now let's look at the data association, right? I mean, we have looked at the detector, we have turned it into a tractor. Let's look at the data association and let's see what we can do in there. So if we go back a few years, including my own work during the PhD, we did a lot of graph-based data association. So essentially how this works is you have your detections in time, you build a graph, and then what you want to do is you want to sort of classify the edges of this graph or solve this graph with some optimization method, so that in the end, all that is left are the edges that represent the connections between detections, right? So the edges that represent the trajectories. And usually how this is done in graph-based data association is you want to put into the nodes some notion of a feature, some information about the pedestrian, right? And this you can do with the feature extraction method. And then you have, oops, sorry, it's going forward, I don't know why. And then you have a discrete optimization method on top that is actually solving the problem for you with the features that you have extracted. And so the feature extraction part, we know how to use deep learning in there, right? We tried it already in CVPR 2016. Essentially, we can compare bounding boxes. We can extract any time of spatiotemporal cues with a neural network, and then input the information in a graph. And this is pretty straightforward if your two detections represent different people. But what about this case, where we have essentially two detections with a neural network that is connecting them with a difference of time step 1, and the same person, so two detections of the same person, but with a time step of distance 2. So what is happening in this case is that how can you actually tell a neural network that this connection is better than this connection, right? For your graph, this is obvious, but for a neural network, this is really hard to say. And furthermore, what we're not taking into account here is the actual optimization problem, right? We have completely ignored the optimization problem and just focus on feature extraction. So what we want to do here is, we want to have a solver. We want to have a deep learning method that goes directly from our detections to our trajectories. That takes into account the feature extraction, so analyzing the image, that learns to perform data association, so takes into account the structure, the graph structure of the problem. And at the same time, we avoid with all of this, we avoid the need to optimize the graph, right? Which is something that it gets expensive, especially as you start having quadratic terms. So essentially, we want to put together the feature extraction and the data association into one learning problem. So how we actually propose to deal with in our CVPR paper is we're going to first construct the graph, same idea of feature extraction with neural networks with the CNN. Then we're going to do a series of neural message passing steps, and finally, edge classification, which gives us directly the trajectories. And you can actually think of this as a feature extraction step, information of the image, and then a learnable data association. Now, the cool thing about this is that you can backpropagate all the way from edge classification to the image. It's not necessarily what we do in the paper because it starts to get expensive, but potentially you can backpropagate all the way. So cool thing about using message passing network is that we can directly work on the multiple object tracking domain, right? We have a graph, we can directly work on the graph. And so any learning that we do is gonna take into account the structure of the problem. And this is, I think, the main advantage in putting together the optimization with the feature extraction. So let me just briefly introduce message passing networks in case someone has not heard of them. I'm sure you have, because this is a really, I think a really cool deep learning tool to work on structures that are not really well defined. For example, like an image, right? So an image is very well defined. It has like all these numbers that are placed in a clear structure. And so you can easily define operations on them. But once you have other structures, like for example, graphs, you have, for example, a graph of a social network, and you suddenly want to do learning there, it's kind of harder to think about what is, for example, a convolution, right? So essentially how message passing networks work is you have your graph, and you have a series of features which are placed on top of the nodes and on top of the edges. So you have features on both sides, both the connections and also the nodes which represent any concept that you want. And then the idea is that you want to perform a series of message passing steps. And you can see here a correspondence roughly between one message passing step and one layer of a classic neural network. So every time that you do a message passing step, you extract some information. So you can see here a bit of a parallelism. And the whole idea is that in this part in the middle, where we're actually performing these message passing steps, we will just be propagating information. So any features that we have here at the beginning, we will just have a propagation, a series of propagation steps in here. And in the end, what we will end up with is a graph with kind of updated features, right? So features that now not only contain information about a node and its own image characteristics, but also contain information about the context, about the neighboring nodes, about the neighboring edges. And so let's see actually how this message passing works. So essentially it's divided into a node to edge and an edge to node update. So here we have our graph. We have the edge embeddings in green and the node embeddings in yellow. And essentially what is happening is it's this passing of information. And the first pass of information happens from nodes to edges, right? So each node looks into the edge that is connected to it and sends some information about its own features. For example, the appearance of a person. And in a second step, we do the opposite, right? So we want to have this communication between edges and two nodes. So all the edges that are connected to a node gather information and send this information to a node. And so here you can see the first problem about working with graphs, because in this case, this node connects to 3 edges. But in this case, this node connects to 2 edges. So we cannot really fix an operation with a fixed size, because sometimes we will have 2 connections and sometimes we will have 3 connections. So we need to have an operation where the order of the edges doesn't matter and also the number of the edges doesn't matter. So what we're going to do then is we're going to repeat these 2 updates, right? Node to edge and edge to node for a fixed number of iterations, which is called the message passing steps. And when we do this, so as soon as we have passed, as we have made one of these steps, the second step already starts to encode higher order information, because now suddenly me as a node, I will have received information from my neighbor, and now I'm passing it to my other neighbor. So suddenly 2 nodes that were 2 connections for every message passing step, we're sharing information to further and further away nodes. So just a bit of notation to kind of clarify how this whole message passing works. We have we need to start with a graph with some initial embeddings, right? The embedding for an edge and the embedding for a node. And then we're going to have essentially embeddings after else steps, which means that the only thing that we're really changing here during the learning process is changing these embeddings. And so the question is, how do we actually do this? So at every message passing step for every edge, the only thing that we do is we gather the embedding of the edge. We gather the embedding of the incoming node and the outgoing node. So essentially every edge connects two nodes. So you just gather the information of the neighboring nodes yourself and pass it through a neural network, which can be, for example, an MLP. And this is going to update the edge embedding for the next time step. So this is basically this step of going from nodes to edge. And the interesting thing here is that we have this learnable function, right? So we have, for example, let's say an MLP, super simple. And the most important part here is that this MLP is going to act on all the edges of the graphs. So this MLP is exactly the same, has the same weights across the entire graph. And this is what makes this thing super powerful, right? Because all the edges of the graph are going to be updated in the exact same way. So now it comes the turn of the nodes, right? We have done the edge updates, and now the edges contain more information, and it's time to update the nodes with the edge information. So it's exactly the opposite. Now what happens here is what I said before, right? So we don't really know how many edges are connected to a node. And that's the main problem here, that we need to actually define an operation that works for 3 edges, 4 edges, 1,000 edges. And this is essentially why, after gathering the information from the neighbors of the node, we have an order invariant, and also doesn't matter how many elements we have in here, we have this type of operation that kind of puts together, like, for example, a pooling operation, right? So any summation, mean, max, anything that you want, that kind of condenses all of this information into what is called a message. And then essentially I'm going to do the same as before. I'm going to take the previous encoding that I want to update. So this would be the node feature. I would get my message, which contains all the information of the incoming edges, and again, the neural network that I want to train. And this, we use commonly an MLP, so it's a super simple neural network. So essentially, all that I've done is pass along information between nodes and edges and have tiny neural networks that tell me exactly what information to keep and what information to discard and how to do these updates. So in the case of tracking, right, we need to start encoding the necessary information for tracking, which is essentially appearance and what we call geometry. Not thinking about 3D geometry here, but of course the node embeddings, like very simply, are going to be a CNN extract a certain features from our bounding box. And the geometry embeddings are going to be relative distance between boxes, relative size, re-ID score. So once we do this, then we go to the neural message passing step, basically gathering all the information, gathering all the information, passing it through our shared MLP, and then updating the edge embedding. Now it's important to note that we actually use these 4 numbers here, right, which seem to be rather handcrafted, right? So here I'm talking about end-to-end learning, and suddenly I'm giving here the relative distance, the relative size. Well, it turns out that this is something that we need to get good performance, right? So this information is really important because, of course, there is a strong prior that a bounding box is not going to change size to bounding box size. Our re-ID score gives us this idea of how similar two appearances are. And we actually use a ReID score because these CNNs here are quite small, right? We don't want this CNN to be huge, and therefore they don't have the power that ReID networks have. So, okay, so once this is done, we go for the edge to node update. And the classic update is what I've explained, right? So all the edge information is found here. You sum it up, pass it through a neural network, and you're done. The thing is that we have a structure. So our problem has a structure. And the structure is the time structure of the graph that is implicit in tracking, right? So in tracking, I have a series of past nodes and future nodes. So to be honest, these nodes here and these nodes here are not the same for the node t of time t in the middle, right? So usually when you have a graph, the graph has no structure and you want to treat all the nodes in the same way. But our case is a little bit different because in our case, we have this temporal structure. And this is not taking into account in the normal edge to node update, which is this one, which just takes all the edge information, sums it up, passes it through the neural network. So essentially what we propose to do is we propose to do what we call a time-aware edge to node, in which we basically separate the update for past frames and for future frames. And with this thing, actually, the performance doesn't increase too much, but I will talk about the constraints later. Okay, so essentially what have we been doing? We have been essentially propagating information, propagating appearance information, propagating geometry information across the entire graph. We haven't even tried to solve the tracking task yet, right? So all that we did was pass along information so that now we know that all detections have talked to all detections at depending on the number of neural message passing steps. We will have talked to nodes far away or nodes which are closer to the node at time t. But the idea is that we still haven't really updated any edge information. We haven't done any tracking or data association yet. So this comes in this step where we actually perform the final task of edge classification. So after all these message passing steps, now we have really good embeddings. And what we can do is we can feed these embeddings to an MLP that is going to predict whether the edge is active or inactive. So we have yet another MLP that essentially tells us whether this is an active connection, should be a trajectory or not. We can train it easily with binary cross entropy, right? We have our edge predictions here. It's important also to balance inactive and active edges. So this plays actually quite a large role. And another interesting thing of the loss is the summation that we do over here. So essentially what we do is we sum the binary cross entropy loss over the last steps, over the last message passing steps. So this means that, for example, if I do 12 message passing steps, I do the first 6, I don't compute any loss. But after these first 6, what I'm going to do for the 7th, 8th, and so on and so forth, is I'm going to do an intermediate prediction, and I'm going to compute a loss on it. So I'm not only doing a prediction at time step 12, but I'm also doing a prediction at 7, 8, 9, 10, etc. And I'm summing up all the predictions. And this essentially makes the whole training more stable and much more robust. Okay, so end of the story is we have classified our edges, we get a prediction between 0 and 1, and now we have to decide what connections do I do. And if you have worked in tracking, you probably know that there are certain constraints when you use graphs for tracking that they have to be verified. For example, that what is called the flow conservation constraint. So any flow that comes in a node is also going to which means the node is active as a trajectory. This connection has to go somewhere. Either you end the trajectory or you connect to another node. So of course, there are certain constraints, not only this one, but other constraints that have to be verified. So if we just threshold the solutions that we get directly from our classifier, it could be that we have infeasible solutions. And so we're going to use a very simple rounding scheme. And this is because we get already quite feasible solutions thanks to the time-aware update step. So essentially with the normal edge to node update, so without giving the solver any information that past nodes should be treated differently from future nodes, then we have that only 82% of the constraints are satisfied. So essentially, this is not really a high number, right? And we're gonna have to start doing tricks to actually satisfy these constraints. If we do the proposed time-aware update, so essentially we treat past connections differently from future connections, then the number of constraints that are satisfied goes up to 98%, which means that essentially with very easy thresholding, we can get feasible results. So another cool thing is to look at how does the accuracy evolve when we actually do more message passing steps, right? So we plot here the MOTA. We plot the MOTA in yellow. We plot the IDF1. And we see the huge jump that we have when we go from 0 steps to 2 steps. And essentially, this is the point where we differ with other graph-based methods, because other graph-based methods, all they can do is get information from neighbors. But when we do already 2 message passing steps, we're already connecting to neighbors that are 2 connections apart. And this is where the performance increases by quite a lot. So in our case, we use the range usually of 12 to 16 message passing steps. But you can see already that with 2-4, we already have a really, really good performance. And this is because this high order information has already started to circulate. So state-of-the-art results, we base ourselves on Tractor quite a lot. And we see that compared to Tractor, we have a very nice identity preservation. So, wow. So when we compare the IDF1 measure, so the identity preservation measure, we improve really a lot compared to Tractor, right? And this speaks for basically the capability that this graph method has in connecting to detections that are further away and start sending, for example, re-ID information, appearance information. So this helps a lot to recover from these small gaps, reduces the identity switchers, and is able also to track trajectories for a longer period of time. So to really cover trajectories. And this is expressed here by this measure, mostly track, which basically says what is the percentage of trajectories that is covered more than 80% of the time, which essentially means you're tracking this person really, really well. And you can see that there's really a jump compared with other methods, like up to 10 percentage points. So there's really a huge increase in the reliability of a tracker. And furthermore, compare with other graph-based methods, we're kind of like an order of magnitude faster. Essentially, we don't have to solve any optimization problem. We just have to do a series of neural message passing steps, which is really, really fast. So we can run roughly at 6 frames per second. Now you might ask, well, if your method is based on Tractor, so essentially we have to first compute the Tractor output and then put the graph on top. How is it that you are faster than Tractor? So it turns out that we didn't use many of the tricks that Tractor++ is using, right? We don't need to do fancy re-ID because we're going to take re-ID. We're going to do re-ID ourselves. And we also improve the code a little bit. So part of this, like most of this speed up comes from just improving the Tractor code. So nothing really fancy here, just to explain what is the difference in the hertz. So you might you might see that this is kind of a favorite topic of mine. I find it super interesting from a research point of view. But there's the huge problem of data privacy. So of course, if you're doing tracking, you're implicitly doing re-ID, Big Brother, following people. And when I, for example, explain my family that I'm doing multiple object tracking, this is the first thing that they say, right? I mean, are you going to follow us with a camera on the street, right? I mean, this is something that they don't like. So essentially, there is a huge discrepancy in how I see my work, right? Like it's super challenging. I'm going to use graph neural networks. It's going to be a lot of fun from a research point of view. There's plenty of applications, right? We have autonomous driving. We need to know where people are. We don't want to, drive over them. Robot navigation. So for me, it's really challenging. But for others, it's this Big Brother scenario, right? So you're going to track me with a camera. You're going to know every time where I am, and this is a huge privacy issue. But the thing is that I don't really care who is depicted in this image, right? So in order to do tracking, I don't really care if this is Mark or this is John. I'm just interested in the label person, right? So it's slightly different when we talk about re-ID, right? But in general, all the labels that we get from COCO, from all these data sets, is just the labeled person, the labeled car. It's not about who is in there or what kind of face does it have or the age of this person. This is not really necessary for detection and tracking. So one question that we ask ourselves is, okay, what if we actually remove the face? If the face is such a problem, then just remove it, right? You can put, you can blur the face, you can put a square on top, or you can put any type of face representation where you cannot identify the person. Well, it turns out, of course, then the performance of a detector drops. Even if you're doing person detection, it still relies on the features of the face. So we cannot just put a square on top. So then we thought, okay, we want to have a method that removes the identities, but detection and tracking performance is still somehow preserved, right? If we put a box on top of a face, or even more aggressively, if we put a box on top of the whole person, then there is no way we can do detection, there is no way we can do tracking. So this is not something we can do. So of course, we want to come up with a method, and you can already see that it's going to be based on generative adversarial networks, right? This is kind of the go-to technique when you want to generate other faces, other bodies. And the goal of our network should be to detect my face, for example, in here, and create something, some output where you can no longer say who that is, but you can still say that it's a person or it's a face. So computer vision capabilities are still kept, but my identity has now gone. So this is the whole idea of our paper, right? In which we want to have an anonymization that removes the identity of a person. It also depicts something that is realistic so that a computer vision algorithm can still work. And here it's important to say that it has to be realistic for the vision algorithm, not for me. I don't care if this looks like a face. I just want my algorithm to say that this is a face. Of course, it has to depict a new identity. We need to be able to control this process of identity creation. And it has to be temporally consistent because we still want to do tracking on top. So let's look at some of the common techniques in order to do this. That one might think, oh, I can do anonymization with this. So the first thing that I can do is I can just put the face of Brad Pitt on top of mine, right? Easy face swap, tons of algorithms that do this. I'm definitely anonymous because no one is going to detect me anymore. It's realistic because a CV algorithm is going to detect that it's a face. But honestly, this is not a new identity. Right? So everything that we did was creating a deep fake. So now suddenly, if I would have an algorithm that really wants to identify and track people, it would say that Brad Pitt was here when he was not. So this is not something that we can really do if we really want to ensure people's privacy. identity. Why anonymization is different from face swapping, for example. And there have already been some works on this. So in order to make this a bit more interactive, I don't know how we're going to do this via Zoom, but let's try. I want to do a small test. These are anonymized faces, and I want to ask you, who do you think this person is? So this comes from the Celeb A dataset, so you know it's going to be a celebrity. If you have worked on that dataset, please don't answer because probably you know who that is, like who the original image is. But I'm going to take some guesses now.
People can unmute them. I can't say because I worked on Celeb dataset.
Okay.
I have no clue. I don't even know what I would guess.
I'm going to give you some more options. So this is all the same person.
Somebody says Johnny Depp.
Nicolas Cage.
Okay, we take Nicolas Cage, first option.
There's Johnny Depp and someone mentioned in the chat.
Okay, Johnny Depp. Oh, I cannot see the chat. Okay, that's good. Okay, Johnny Depp, Nicolas Cage. Any other options? Okay, we're gonna go with those two.
There's Tom Holland. Somebody mentioned
okay.
Tom Holland.
Okay, I don't even know who that is, but okay, I'm happy to have a third option. Okay, so this is one anonymization method, and this is a competing anonymization method. So this is an anonymized face. Out of the three options, or any other option, what do you say?
Nicolas Cage.
Okay, so to be honest, it looks like it's Nicolas Cage, right? Well, it turns out I'm quite happy because this is a competing method that was published in ICCV 19. It's about de-identification and anonymization. And they have a different goal there. And the idea is to anonymize more or less a face. But to be honest, even the more anonymized version of Nicolas Cage still looks like Nicolas Cage. So I'm kind of happy to say that our method has stronger anonymization capabilities. And again, I have to say that it's very different whether a method anonymizes for neural networks or anonymizes for a person, right? So I have to say that the anonymization in terms of a neural network trying to identify these faces is not too bad. But visually, it really looks like Nicolas Cage, right? So these are two important aspects to keep separate because it's not the same what a vision algorithm sees and what a person sees. Well, let's talk about our method, which I think does better anonymization. So another thing that we need to do is we need to have some sort of control. And by control, what I mean is that we want to be able to control the anonymization process so that whenever my face comes in, it's not always reconstructed as the same person. If that were the case, then I would be able to still track myself through multiple cameras through a city, and eventually, given the patterns of my motion, maybe even identify myself. Right, so I want to have a control that if now I want to put a different identity on top of me, I should be able to do this. Okay, so our method, which we term CIA GAN, it's for conditional identity. Wait, how was it? Conditional. Oh my God.
Conditional identity anonymization.
Cool, thank you. So I just remember the acronym because it's kind of cool. But the whole idea is that we're going to have this autoencoder type of network, right? This UNet that is going to take an input face and it's going to separate it into the background. So we're just anonymizing the face, and we're going to take off the face only certain key points, certain landmarks. And the idea here is that we don't want to leak any face information, any appearance information, but we still want to keep the pose of the face or the pose of the full body. So we need to have these landmarks. idea is, first of all, the image needs to look real, right? So we have the classic GAN laws to determine whether this is real or fake. This is going to create the nice looking images. But the interesting thing that we do is to have what we call the identity loss. And this identity loss is basically what is going to allow us to give, some control over the generation process. So if we look a bit more detail into what we do is, we take a real set of images. We have certain identities, in this case, these celebrity identities. And at any point in time, we can choose one identity at random and infuse this information into our autoencoder. And then from the output image that we generate, what we want is that the embedding of the generated ID is essentially the same as the embedding of the real ID. So we want that for a neural network, this ID that we plugged in here is the same as the ID depicted in here. And we're going to use basically an identity discriminator for this. So we just want to bring these two embeddings closer together. And so essentially what is happening here is we're of course not recovering the identity that we have fed in, right? But we have essentially mixed the initial identity with one of these random identities, right? So we don't allow it to really reconstruct the identity that we feed in, but rather have this nice mix of two identities. So the advantage of this is that we have full control over the identity generation, and we can then generate, for example, different identities when the camera changes, preserving the privacy also across cameras. So for multiple object tracking, what we would do is we would apply the same transformation for all pedestrians in a frame, right? We still want to do tracking. So for every pedestrian, we choose identity 39, and we transform all pedestrians with identity 39. Now, what happens for a different camera is we want to apply a different transformation, right? We don't want to have this long-term tracking, even if the face cannot be readily identified as my face. I don't want to be tracked across cameras in a city. So we can just use a different transformation for a different camera. And then the long-term tracking and the potential misuse of data is gone. So here are some results of what we can do when we have the source image. So this is the input image and the random identity that we picked. So you see that it's kind of a nice mix, right? It still preserves the pose again because we have the landmarks, but it tries to infuse a bit of the identity of the other person inside this pose. And this creates this kind of funny looking mix that allows us to basically not identify it as either the source nor the target identity. And so, of course, the most important thing for us is that we cannot identify the person, right? So we try with a couple of methods, and we want the identification to be as low as possible. But at the same time, we still want to detect the face, right? So for example, if we do pixelization, the identification is really good, right? I mean, you're not going to identify anyone from this image at the bottom right corner, but you're also not going to detect it as a face. So suddenly I have gained anonymization, but I have lost the detection power. So essentially what we want is to have good detection, as we have, above 98%, and really, really low identification. And so these are some of the things that we can do. We can also, remove glasses or remove facial hair, and it works actually reasonably well. So the resolution is still low because we work on the CELEB A dataset, but even for the raw resolution, it still works pretty well. And we also tried to identify only by the hair, because you say, well, the hair is the only thing that you're not changing. But it turns out that still only with the hair, it's pretty difficult to actually detect which celebrity it was. So anonymization is still quite powerful, even if the hair is still there. So it seems that methods tend to focus more on the face. And of course, we have tried on a different domain, which is essentially what we're interested in, which is to actually anonymize full bodies, right? So this still is, we can anonymize people by keeping the pose, which is very, very important if we want to do tracking, pose estimation, anything with those images. And this is currently the what we're pursuing more to basically increase the quality of these anonymizations. And it turns out that even without infusing any temporal coherence, the temporal results are pretty good. So we can do tracking, we can identify the identities across the videos across the frames in a video. And so the temporal consistency works actually surprisingly well. Okay, so I hope I didn't run too much out of time. So in this talk, I wanted to cover kind of two aspects of tracking, right? The first one was how to get closer towards end-to-end learning in tracking and how to really leverage the power of machine learning in tracking. And for this, I have presented two works, one that pushes the detectors as much as possible, not by just applying them on a frame-by-frame basis, but by really taking the easy scenes and solving them with a detector. And the second one is to move closer towards working in the natural MOT domain, which MOT can be represented as a graph. So working directly in the graph domain and taking into account the structure of the problem is actually a huge advantage and improves the accuracy by quite a large margin. And secondly, the last work that I presented is, I find it really interesting because in MOT, we should really start to look into data privacy. So we have worked a lot on benchmarking, and we're getting actually quite a lot of problems when we release the new data set. You know, is the privacy of the persons in there actually preserved? And a lot of our data sets, especially the multi-camera ones, have been misused by certain governments, for re-IDing people, by tracking them. And so I don't know if you know the Duke MTMC dataset, which was hosted by Mod Challenge, and they had basically to take it down. So this is one of the problems that an algorithm that looks into data privacy should be able to deal with, essentially. And last, I want to do a bit of advertisement, right? So we've been working hard on Mod Challenge, not only on multiple object tracking, right? So we have pushed also multiple object tracking by releasing these kinds of absolutely crazy scenes for the 2020 edition. So I think this is a really hard task, and hopefully this will keep us busy for some years. But we're also working on other types of challenges, right? So multiple object segmentation is a challenge that we have released recently. We also have a CVPR workshop. We're working on expanding to other domains with other collaborators from biology, for example. And we're working on a synthetic version of Mod Challenge, which would hopefully get rid of the privacy issues of the manual annotation, which is really tedious, and would hopefully bring also a big step forward in the field. And of course, we're also working with some people here from CMU into integrating this cool data set that you have with a variety of objects. I think this is also a really, really interesting venue to look forward to. And yeah, I want to end by thanking, of course, my collaborators, students that are working really hard for all of these projects. And thank you also for your attention.
So thank you, Laura. We have time for a few questions, and Laura has been gracious. She gave us like next 20 minutes for any open discussion or anything about tracking. So you can raise your hand or unmute yourself, and then we can ask the question and start the discussion. Dave, yes.
Yeah, I had a couple of questions. One is, I might have missed something with the privacy part, but if you are changing all of the faces to be the same identity, how do you take advantage of unique appearance properties of the face to help with tracking?
wait. So you mean this, what I'm saying here, right?
Yeah, essentially, yeah.
Okay, so the thing is that, so how the identity preservation works is so the loss is indeed defined such that I want to recover the exact same identity as I had here as input, right? So you might imagine that if here I say Brad Pitt, then all the images that I will reconstruct are going to look like Brad Pitt. But effectively what this is doing, right, we're balancing different losses. We're balancing a gun loss, we're balancing this loss, and we also have a very, very strong prior as input, which is the landmarks. And so what essentially we do in all this optimization is that we're mixing the two IDs. So we're mixing the ID of the input, where we input the landmark and the background, and the ID that we feed in here. So even if for all the frames I choose Brad Pitt, essentially what I'm going to have is me plus Brad Pitt, the other pedestrian plus Brad Pitt, but still it's going to have a unique appearance. So I'm still going to be able to do tracking.
And what's the part that keeps it looking like you and not Brad Pitt? Is it the hair or?
No, I think this is mostly the input of the landmarks, right? So we still have, for example, the shape of the face that is quite preserved, or the, for example, the nose. And it's also the idea of, it's also the gun loss, right? Because the gun loss knows how this appearance should look like. So I think it's kind of trying to also have reconstructed in order to make it look real.
But isn't a picture of Brad Pitt would also look real, right? That would also optimize the GAN loss, no?
Yeah, that's true. That's true. I think it's mostly about also the landmarks, right? So I mean, you would need to change the shape of the face quite a lot to make it look like Brad Pitt, and it's kind of easier to in-paint some features of Brad Pitt. And the other thing is that we don't want to push this loss too much, right? So you also need to have to work by balancing this loss so that it doesn't really become too powerful, because then you might run into the problem of really recreating Brad Pitt.
Right. Okay. Thanks. Yeah.
Another question? Sinshu.
Hi, Laura. This is a question from Sinshu. I have two questions. And first, this is great talk. Thank you. My first question is about your CVPR 2020 paper. I noticed that the performance of the message passing network gets reach the highest limit up to certain level of snares, basically about 3 or 4. So we actually have a very similar CVPR 2020 paper using similar technique on that topic, and we have the same observation. So do you think, is there any potential reason that you have causing that limit in the performance?
So I think this is, after a certain point, you probably, it doesn't make sense to share information of nodes that are, I don't know, 10 steps away, right? And this is because you also have the graph structure to take into account. So at some point, of course, the closest neighbors are going to have more influence. And unless you have connections that are really far away, like 50 or 60 time steps far away, you're not going to really gain much from doing all these message passing steps, right? So I think the real power lies in recovering the small occlusions, and the small occlusions are typically up to 10 frames, I would say. More than that, first of all, it becomes a huge graph. And second of all, I would also doubt that the message passing steps would be enough to actually make these super large connections.
I see. Okay, good point. The other question is about the Tractor paper. So you have very good analysis about which part of the problem is the MOT that we should really take care of. Basically, the part, the data that has the partial occlusions, the mostly nice in the middle of your graph. So there's another paper called Fair MOT. towards it's called a baseline for multi-object tracking, recently published on arXiv. So they show another big improvement, basically another 10 point in MOTE and also IDF1 numbers. And I guess the main reason is because of the much better detection performance. So they don't really do a very much different in terms of data association. So they use the exact same like ReID and a simple motion model, something like that, but not much different in the data association part. But the performance increased a lot. So I'm wondering, is it really important to focus more on data association for the partial occluded data? Or is basically maybe we just need to further improve the detection performance, and then we can just, this kind of difficult data can become easier for data association. So basically, we don't need to push much harder in that data association direction. What do you think?
So the nice thing, so I've seen the paper, I haven't read it, but Solid had a similar intuition to Tractor. And this was exactly the point that we wanted to make with Tractor, right? So any improvement that comes from detection now is also an improvement in tracking, direct contribution, right? So we don't even need to do anything in there. And so the idea is to say, okay, I want to push as much as I want from the detection side, as much as I can from the detection side, but I'm also going to reach a point where I cannot improve anymore, right? I have my occlusions, I have my small pedestrians, whatever illumination changes, I cannot do detection there. And the point of Tractor is that you should focus on those cases for tracking, right? I mean, that is the whole point. So I'm happy actually to see more works that are pointing to this direction. And of course, Tractor accuracy is not the end. But the cool thing is that a new detector comes in, you can Tractorize it, and then you can put a graph on top and further improve it, right? So the nice thing is that we can keep improving tracking by using both of the paradigms, basically.
Yeah, that's true. Thank you.
Yeah, thanks.
Achal.
Yes, I guess a related question. So it seems like a lot of tracking improvements tend to come from detection improvements, and this is so there's kind of two philosophies on this. There's the kind of, I guess, what I would think of as the old Mach challenge philosophy, which is you treat tracking as like a problem that you do on fixed detections that you kind of freeze for everyone, as opposed to this newer philosophy where we're actually improving the detections themselves. There's something nice about the first version because you're kind of separating the detection problem from the tracking problem and seeing how well you're improving. I'm curious if you have thoughts on like moving forward, which land we should live in, or if
that's an excellent question, because actually, like, a lot of the Tractor paper was spent on convincing people that we were still using public detections and that can still be considered as a public method. And then, of course, we started wondering, well, before, like in 2014, when we created the benchmark, like everyone was doing like super dirty tricks, right? Like I get 2 or 3 sequences here and there. I use whatever detector, whatever threshold, I don't care. I put my tracking on top. The evaluation was also different thresholds. And now suddenly you could not really tell why the performance was better, right? So the idea of fixing the detections was to say, well, if the problem is really tracking by detection and everyone uses this paradigm, then at least let's take the detection and go towards tracking, right? Now, of course, things change, and well, this is partially our fault for introducing Tractor, right? And we're also thinking how to evolve, right? So we have been working with a group in Aachen University in Germany in a new metric. So the idea is that this new metric should reflect more of the tracking capabilities and less of the detection ones. So we're still going to have some residual detection performance, right? Because essentially, if you use detections, or let's say, if the detections are better, you're going to have an easier job at tracking, and you're going to be able to track smaller pedestrians, more pedestrians. So there's always going to be a detection aspect in there. But we now have created a measure that is much, much less correlated with a detection measure. Because if you look at MOTA, essentially are the same. I mean, detection is equivalent to improvement in tracking, and that's it. So clearly, this is not a good measure, and we're working on it. We have submitted now a journal version. So if you're interested, I can send you a copy. So it's not super straightforward to explain the new metric, but I can send you a copy so that you get an idea. But the idea is, yeah, to evolve also the benchmark, to evolve the metrics, so that we kind of reflect what we found out in the Tractor paper.
Awesome, thanks.
Another question? Any other question? Meanwhile, Chris, yes, Chris, you asked?
Oh, sorry.
Oh, Dave, yes.
Yeah, I just had a general question actually about graph convolutions. Since you spent a lot of time talking about them in your talk, I guess you might know the answer to my question, which is that I was wondering if there's any proofs about whether it converges if you run it for a very large number of message passing steps. Is it like guaranteed to converge to certain like node activations and edge activations, or is it possible to diverge, or can you say anything about that?
So I don't know about the theoretical aspects of conversions. These I cannot tell you, but it depends a lot on the graph that you have, on the connections that you have. So of course, more connections means you're going to need more message passing steps to get a stable embedding. In our case, it doesn't take too much, and this is also because the graph is quite simple, right? So whenever the MOTA and IDF1 measures kind of get stuck, it's also because the embeddings start to get stuck or fluctuate in a meaningless way that doesn't change classification. But I would need to check actually for the theoretical guarantees of that. I cannot tell you straight away.
Okay, yeah, thanks.
Any other question? Yes.
So I have also a question.
Yeah.
Data privacy setting. So have you tried to treat it as a hyperparameter, the identity of that you are using? So, for example, if you want to improve the actual results that you're getting, maybe you can treat it like a hyperparameter and try to find an identity that gives you like better results.
Oh, okay, I see. That's a very good point. So we have seen it's not a really nice study where I can tell you the exact numbers, but we have seen that there are some identities that are better at anonymization, right? So some of the Asian identities work really well, probably because then it's really hard to detect. Let's say the original face if you have Asian features, right? I mean, as soon as you change the race, then things start to work much better. In our case, we didn't want to do this. We didn't want to on purpose use a specific identity for anonymization because we wanted to see if we randomize this, what is the performance that we get, right? So we're interested in seeing the overall performance rather than a really controlled performance. But of course, for a real scenario, it would be interesting to choose the identity that would yield better results, right? And these I'm pretty confident that we could do with some simple measure, some simple similarity measure, for example, or for example, choosing an identity where the embedding is really far away from the original identity, something like that.
So one question which I have and goes back to what Achal was saying about detection, and since you also pointed it out, isn't it true that a lot of tracking sequences that we have is tracking human sequences for very well positioned cameras? Now, if suppose I go to certain categories where the detection is not so good, highly non-deformed category, highly non-rigid categories, will we have similar conclusions? I mean, I'm just saying, say current setup is humans on street scenario. Let's say there's a structure to the humans, and so detection works pretty nicely over all these scenarios. But let me say my camera was in a very different position than what is generally seen, and I am looking at a very different object where detections are also not that great. Now, one can say the right benefit of tracking would be that, okay, you do certain detection, but then the association over time will give you much better performance for the detection also. And can also act as a source of a data set or data augmentation if we think of association in that perspective. Now surely for the sequences that we have, detection is giving a lot of performances, but just trying to think over here, what if we move away from the human scenarios? What if we capture some other categories where the detections is also not working, from very different camera perspectives, which is not available in COCO also. Say COCO has general bias of a photographer bias, where generally you'll see cameras held from this particular view or maybe top or aerial view at the max. But let's say I change the camera view from bottom up, and kind of changing the camera views arbitrarily now. My gut feeling says tracking is going to fail badly in all those scenarios. Not tracking, detection is going to fail badly in those scenarios. And we need some measures of association to be able to do well on those challenging sequences. What would your take be on that? Or how should I even properly formulate my thought if I have to think in this direction?
Okay, I see what you mean. That's actually a good point, right? So the main reason why Tractor works is because detectors work really well for mode challenge, right? So as soon as your detector fails, I think this would also be an interesting scenario to explore, right? Because then essentially, the only thing that you can look at is motion consistency. So we're looking more into things like optical flow, motion clustering, all of these kind of low-level tasks which try to look at, for example, the motion, and only with the motion you can define an object, right? Because the appearance is telling you nothing. So then I would probably phrase it more in those terms, in terms of motion clustering, looking at low-level optical flow, and trying to disambiguate the motion and not the appearance, if the appearance is really so bad, right? So this would be a completely different scenario that would, I think, be like really pushing for tracking. Although I don't think it would then be object tracking, but rather motion analysis at the pixel level, right?
Right. Right.
Kind of relatedly, one thing that's that I still can't really understand is we always talk about detection helping tracking, and at least intuitively, it seems like tracking should be helping detection. We don't seem to have gotten to that point. Maybe that's just because detection works so well.
I think so. I think tracking can only help detection when there's like a really strong problem in the image, right? Like occlusion or crowded scene. So like everything looks like the same person. And then, for example, non-maximum suppression would not work, things like this. And there are not so many scenes like this if you think about it. Like in mod challenge, there's very, very few scenes. I mean, it was discussed extensively about trying to track the occluded pedestrians, like with I forgot her name, but there's one student working on that, and honestly, there's just few samples like this. So whatever gain we get from that, we just don't see it in the metrics, but it doesn't mean that it's not there, right?
Yeah, maybe one reason for what Achal is saying is the problems with the data set. I mean, human performances are also already, like, we really already have very large data set for human performance, for human understanding or human detection. And so there's not much of a win that we are going to get from the tracking algorithm that we already don't know. But suppose there is some categories in the tail, and can we really utilize the tracking to improve the performance for those categories? Now there's a chicken and egg problem over here. Okay, first we need to get the data for those categories, label and those. Okay, if you get the labels, then maybe you can get a better tractor or detector over here as well. So I don't know how to answer that thing, but I think maybe it might be better if we start moving. I mean, though I really care about human events, but understanding say detection algorithms and to disambiguate the differences between detection and association, some non-human categories which are challenging, like birds.
I mean, I think that it's still good to have human benchmarks, because humans, as you said, are super important, right?
Yeah.
So for any application, the object that you want to be able to track best is probably a human, especially for autonomous driving and so on. Now, the other thing is that if we would focus on other categories and on categories for which we don't have an object detector, for example, then we would for sure improve tracking, which would improve tracking also for pedestrians, right? So probably we need both, but there is a huge problem in annotation. And I always talk about two levels of diversity, right? So there's the appearance diversity, and this is what basically image benchmarks do, right? They try to get, for example, chairs with different appearances. Now, suddenly we are working with videos and we need to have appearance diversity and also temporal diversity. So the same chair moving in different ways. So suddenly the number of annotations that you need to really capture both diversities is huge, right? So I think there's also an annotation problem, and this is also why we're going a bit more into synthetic data, right? Because this might give us a possibility to actually, just sample a bunch of diverse scenes and not have to worry about the annotation, which I think is a huge problem for video data sets.
Right. All right. Are there other questions? If not, we should thank the speaker. It's already late in Germany.
A bit.
Thanks, Laura, once again.
Yes, thank you for organizing this. It was really cool.
Thank you very much.
Thanks so much.
Thank you.
Thanks.